Okay, so now we're going to be looking at the hmm, we're going to be looking at gravitational field strength, right? So field strength at a height above the Earth's surface. So what are we talking about there, right? So we spoke about gravitational field strength already, right? As we move away from the Earth's surface, so let's say that this is the Earth's surface here, right? As an object moves away from the surface of the Earth, right? The gravitational field strength starts to decrease. So the gravitational field strength G, right, starts to decrease. Okay? So we have that. So the gravitational field strength at a distance r from the center of the Earth is given by this. So we have G is equal to the gravitational constant times the mass of that object, right, divided by the distance there, right? So this is where G is the field strength. Well, we know what G is, right? We just stated what G would be, right? But G really is the gravitational field strength, right? At a distance r from the center of the Earth. Okay, that's what G is, right? That means that the big G now is the gravitational constant, right? M is the mass of the Earth, right? And then R is the distance between the surface, or the distance from the center of the Earth. So R is the distance from the center of the Earth. All right. So that's what we're working with right now. So that's the equation that we're working with. So at Earth's surface, right? At the surface of the Earth, let's just note this. So at the surface of the Earth, right? So let's say that this is the Earth's surface. Earth's surface, right? R is going to be, right? So R, Earth, is gonna be equal to around 6.37 times 10 to the 6th meters. That's the general diameter, right, of the Earth. So I can't put it at equal actually. I have to put it at roughly equal. So it's approximately that value, right? As the height r increases, right? So as the height increases there, we are gonna have the distance from the center of the Earth plus that change in height, right? So as height increases, right, we have the h there. H is the height above the center of the Earth, or above the Earth's surface rather. Height above the Earth's surface. So we have that. Alrighty? That's R. So that's what we get there. So hopefully this makes sense, right? Therefore, the gravitational field strength, right, at a height above well, or a height above the Earth's surface. No, gravitational field strength at a height above the Earth's surface. So it's a height above the Earth's surface is going to be equal to G, which is gravitational constant, times M, which is the mass of the Earth, divided by the distance, Earth, right? The radius there. Well, not the radius, but yeah, the radius actually, right? Times H squared. All right. So let me change these to little r's because I don't want to confuse anybody wondering what big R is. But R is distance. All right. So that's what we have there. So what we're seeing here is that in order to get the gravitational field at some height above the Earth's surface, right, we're gonna be using the same equation that we derived up here, right? But R, right, is going to have some added value because what we're doing, looking at R is a distance towards the center of the Earth, right? But if you are not at the surface but somewhere above the Earth's surface, we have to add that H, that height H, right? And then we square that, and then we can use that to divide GM, and we should be able to get that there. Right, so the relationship shows how the gravitational field strength decreases as the distance from the Earth increases. All right, so G is inversely proportional to distance from the Earth. That's what's happening there. Alrighty, all right. So, and we stated, or we were looking at earlier, right? So let's look at this now. Our question. Let me hold here for a moment. Are there any questions? Are there any questions before we move on to circular orbits? By the Alrighty. Give me one moment. Let me reconnect to the meeting with my phone. So I got kicked off. So if you have any questions that were in the chat, you could just copy and resend them like around now. But yeah, so hopefully there are no problems. Okay. Alrighty, so circular orbits now. Looking at circular orbits, we can move into right using our forces that we looked at, right? So for circular orbits, right? Notice that this is circular motion. This is circular motion, right? So for an object to stay in circular orbit, let's say that the sun, right, and the earth is in a circular orbit, right? For an object like the earth should to stay in circular orbit around the sun, for example, or a moon around a planet, right? The centripetal force needed to maintain its circular path, right, must be provided by the gravitational force, right? So the circular force needed to maintain the orbit. Remember this, the force acting on an object here, this force versus the velocity here v. This force here must be or derives from the force of gravity. It is gravity that is keeping the object in orbit as it moves centripetally or circularly around. So that's how we maintain an orbit. Alright? So we can note here now that F centripetal force is equal to the mass times velocity squared over r as we got circular equation circular motion, right? Where v is the orbital speed, right? So in this case, v is the orbital speed, and the r here, right, is the radius of orbit. All right, m will be the mass, f centripetal is centripetal force. All right, so we have this. So we have that as a centripetal force, right, of an orbit. So the gravitational force now, so the gravitational force now is F gravity is now equal to G times the mass of an object. Let's say the Earth. We're looking at the orbit. Let's focus on the orbit of the moon, right? So let's say we're talking about Earth, right? Because that is what we're called to do in Cape Physics, right? This is the moon, right? So in order to get that now, that would be the Earth around anything, right? Or the moon. We're just looking at the force, gravitational force, right? So it would be G times m of the Earth, right? Times m divided by r squared, right? So we have that there. Okay? So the mass of the Earth times the other mass. That's what we're looking at. So remember that gravity, G m1 m2 over r squared. Remember that? We're just looking at the gravity with relation to Earth now. So Earth, we're looking at the gravitational force between Earth and another mass. So m, small m would just be another mass out there, right? So you could plug in the sun's mass and then find the gravitational force between the Earth and the sun, provided that r is the distance between the Earth and the sun. Okay? So hopefully that makes sense, right? For an object in a stable orbit now, the forces, right, of the centripetal force and the gravitational force must be constant. So let me write that. Let me note that for anybody who wants to hear. All right. So for an object in a stable orbit, right? F centripetal. So centripetal force must be equal to the gravitational force, right? That's what we're talking about. So in order to maintain a steady orbit, the gravitational force must equal to the centripetal force. In other words, we are saying that mv squared over r is equal to g m of the Earth m over r squared. All right. So if we were to find the speed, we were trying to find the speed, orbital speed, right? So finding orbital speed, v, right? We have to cancel the m, right? So finding orbital speed v, we have v is now equal to what? Let me do everything. Let's not do it that way. V squared over r is equal to g m of the Earth m over r squared. We end up cancelling over here. So let's say that we minus m from this side. We minus a small m from this side, so cancelling out the m, right? So we end up with this. V squared over r is equal to g m of the Earth m over r squared. Still, we want to isolate v. V is what we're looking for, right? So we times by r over this side, we times by r over this side. We end up getting v squared is equal to r g mass of the earth times the other mass over r, right? Well, let me remove that. We got rid of r already, right? Therefore, v is equal to the square root, right, of g mass of the earth over r squared over r. All right. So we end up with that. Thus, we can state that the speed required for an orbit to maintain a circular orbit depends, for an object rather, to maintain a circular orbit would have depended on the Earth, right, and the radius of the orbit, right? So we're just looking at that. So in order for something to stay in orbit, these are the equations that we use, all right? So that is what we have there. Before we move on any further, do we understand what was happening up here as I took you through it before we start talking about apparent weightlessness and geostationary satellites? Okay, so we understood that what was happening up there. All right. So for apparent weightlessness, what are we talking about when we discuss apparent or when we're discussing apparent weightlessness? Right? So let's look at this. So for apparent weightlessness, right? When something is in orbit or when in orbit, right, we could say that the astronauts, right, actually experience some weightlessness. So we've seen it on TV, we've seen it in cinema, right, as I stated, right? We see it generally just in cinema or pop fiction, right, or science fiction, right? So we see weightlessness, right? Because we can state that they are in free fall, right? So they experience apparent weightlessness, one, because the astronauts they are in free fall. What do we mean by that? They're falling towards the Earth, but never hitting due to a tangential speed, right? So they're falling towards the Earth. They're falling towards the Earth, right? But not hitting the Earth, right? But not hitting due to tangential speed. What do we mean by that? We're saying here now that around the Earth, right, when the astronauts are moving around the Earth in some vessel, right, yes, they are going to be falling towards the Earth, but due to their tangential speed, all right, remember their orbital speed, tangential speed, v, right, they're not going to actually be hitting the Earth. So it's like they're continuously falling towards the Earth, but they're never actually hitting the Earth. So it's something like this, continuously falling towards Earth, but never hitting the Earth because of their tangential speed, right? So that's why they experience this apparent weightlessness, right? Since both the astronaut and the aircraft are falling at the same rate as well, the astronauts will feel no force, no normal force, right? Giving the sensation of weightlessness, right? So that's what's happening there. So they're constantly falling towards the Earth, right? But because of their tangential speed, they don't actually hit the Earth. Alrighty? So looking at that. So hopefully all of that is fine. Alrighty. Are there any issues or concerns?